right, the whole idea of error, which is our final thing, when we start talking about Taylor, what's the purpose of creating a Taylor polynomial? To approximate any function easier. So whether the function is trig or log or exponential or square root or any function, and we are going to approximate it with Taylor's polynomial. And you start out, if your Taylor polynomial is only 2 terms long, it won't be that accurate. If your Taylor's 3 terms long or 4 terms, the more terms you have, the greater the accuracy. The greater the accuracy, the less the error. So now we're talking about the opposite. We want to know what the error actually is. How close is it? Is it a perfect match? Is it a match to 9 decimal places? Is it a match to only 3 decimal places? Like, how close is it? And there's 3 ways to calculate error. And the 3 ways are going to be whether or not you recognize the type of series you're working with. So the first way we'll talk about is there's one way to calculate error if it's a geometric series. There will be another way to calculate error if it's an alternating series. And then the final way will be how do you find error for any kind of series? So anything that will work. So some people might say, why don't you just teach us the any series? Because it'll work on all of them. And that's true. You could just learn what's called Lagrange error. Lagrange is another French guy, French mathematician. We could just learn that. Just like your math teachers could just teach you the quadratic formula, because the quadratic formula will work on any quadratic equation. But it is helpful to know how to factor, because sometimes, a lot of times, factoring is easier. Even though factoring doesn't always work, but when it does, it's easier. And so that's why we show you all 3. I'm going to show you all 3 because although Lagrange would work all the time, it's not the easiest one. It will be much easier if you just recognize geometric series, and then even easier if you recognize an alternating series. All right, here we go. So, again, this is a very intimidating thing to look at until you know what it means. This, again, is just the symbol of how we've been finding Taylor and Maclaurin series. Remind me again from last week, what's the difference between Taylor and Maclaurin? Maclaurin is focused on 0 being at center. Taylor can be anywhere along the curve. So Maclaurin is a type of Taylor, but very specific. So this is how you form either of them. All right, what does this part represent right here? And Christian can't answer.
The original function to increasing derivative.
Okay, so these are the derivatives, or the derivative family. Okay, so that's where you put your derivative in. All right, this part is the part that makes it a polynomial. So that's your polynomial position, or polynomial piece, centered at A. And then finally, we have our factorial piece, which also changes as the term changes. All right, so again, the more terms of the polynomial, the less and less error there will be. We increase our accuracy. So how far is far enough? How far do you have to go to be reasonably satisfied that your answer is going to be accurate enough? Okay, that's the question we want to answer today in terms of how much error is allowable. So to answer the question of how far is far enough, how many terms do we have to go, we need the vocabulary word in English, truncate. Okay, this word means to cut off, or to splice, if you know that word in English. Okay, to separate one from the other. So if you're part of a friend group right now, as you head off to college, your friend group will separate. You're going to go in different directions. And so that is how we use truncate here. When we truncate things, you are going to be told, well, sometimes you are told and sometimes you have to figure out, where are you going to separate this? Are you going to separate it after the 3rd term and then separate everything else? You're going to separate it into 2 pieces. That's called truncation. And so one side will be called the polynomial piece. And what you cut off from that is called the error side. The polynomial piece will be a finite number of terms. So say truncate after the first 4 non-zero terms, or truncate after the first 7 non-zero terms, or whatever. And then the error is the other part. That polynomial is what we call finite. Finite because it has a specific number of terms that come to an end. The error is infinite. It just continues on and on and on and on and on without end, but it's getting smaller and smaller and smaller and smaller. So again, let's imagine that we're going to truncate right here. We have a finite polynomial, and we do p sub k of x, and we have an infinite error. The rest of the terms are what we define as the error, and you'll call that e sub k of x. If you truncate it after the third term, then this would be p3 and e3. If you truncate after the fifth term, it would be p5 and e5. That's how the notation is going to go. If you want to get the error by itself, so go ahead and we're going to put that this is the sum. If the polynomial ends at k, then n would start at k and go all the way to infinity. That'll be your error part. So we define error. If you wanted to get error by itself, you have to subtract the polynomial to the other side. So error ends up being moved the whole piece over. So you would take this part and subtract it, and you're going to subtract it over to the other side of f of x. And by definition, we always want this to be a positive number. So we're going to throw absolute value bars around it to make sure that when we subtract it, we always get a positive amount of error. We say it's off by 3%, or something like that. But you have to understand that could mean it's 3% too high, but what could it also mean? It could be 3% too low. And so it's going either way. Just like we saw in intervals of convergence, it was an absolute value, and you'd have, we're going this way and that way. Okay, we're going both directions. Sometimes it's just as easy as doing simple subtraction. Most of the time it's not. Okay, but sometimes you get lucky and it's simple subtraction will work. I don't need to tell you anything about that slide. Okay, so let's go here. All right, if you truncate a geometric series, okay, if you truncate a geometric series, okay, so let's imagine that we are truncating it right here. And say, all right, if you decided to cut it off, would, how much would your error be? So the error is on this side, and your polynomial is on this side. A geometric series truncated is two geometric series. You have a small geometric series. This is still geometric. And this one is also still geometric. When you truncate a geometric series, its error is all still geometric because it's still following a pattern of multiplication. The p part, the polynomial part, it has what starting term? The p part. What's its starting term going to be? Do you know it's 0? It'll be a1. Its starting term is a1, okay? The error part of it, what we define as error, what's its starting term? In general. This is this one's starting term, okay? And I have 3 terms into it, a1 times r, and a1 times r squared, okay? The E sub k, what is its starting term? It's this, right? I'm not trying to trick you. I'm just asking you to tell me where it's starting. Okay? So it's starting at a different spot. So the formula for that still follows your summation formula for geometric terms, where the first term goes here and 1 minus the ratio goes here. So in this case, the first term is this one. It's the one that starts the error, and then 1 minus r. So your numerator changes because you're starting at a different spot. That is the definition for error when the thing is geometric. You just start at that term, and that becomes your numerator. So that's our, yep.
Would this work for geometric power series?
If it was a power series, then we would have r of x. And then this one, let me see if I can adopt that. Be r of x to the k. All right, so the geometric series starts with the term after you cut it off. Okay, it's the term right after you cut it off. Actually, so let's go back. This is actually k plus 1. If I'm cutting it off at k, then error starts at k plus 1. It's the next one after I've decided to chop it. So that was, I guess, what I intended for this to be here. Here's the formula. So we'll put that a times r to the k plus 1 over 1 minus r, whatever r happens to be. So let's actually just do one. I think it'll be easier. All right, here we go. This is your geometric series. So we know that our geometric series, if we spread it out and for a little bit, okay, what is this geometric series going to start with? 1. Good. And what's its r? X squared. So what will the next term be? X squared. And what will this next term be? X to the 4th, and then x to the 6th, and then, all right, so this is what we're working on, etc., etc., dot, dot, dot. They tell us to truncate this after if we use 4 terms. So I will be truncating it right here. So my error is going to start on the other side of the truncation sign. So the formula for the error, because this is geometric, is x to the 8th, because that's where I'm starting, over 1 minus x squared. And that's it. That's the formula for the error. Okay, if I asked you to use, the first 6 terms, and you truncate it after the 6 terms, and then the error is going to start with the one after that. Okay, any questions about that? Okay. All right, here's another one. Find a formula for the truncation error if we use P5 to approximate. All right, so my function is going to start with the number 1, because that's the first term. The r is 3x, so this would be quantity 3x to the first, and then 3x to the second quantity, third, fourth, fifth, etc. Okay, we just keep going. After what term do I truncate this?
3x to the 4th.
Okay, it doesn't say the first 5 terms. It says P5. Yeah, because this one is your P order 0. Because that's, remember, n starts at 0. Okay, so it's different if it says the first 4 non-zero terms, then you count that beginning term, because we're just counting the first 4. But when it tells it to you in P terms, you got to remember where the terms, how the terms count, that we are starting with n to be 0. So we're going to truncate it here. So my error is going to start on that side. So then by definition, my error would be quantity 3x to the 6th over 1 minus 3x. So that'll be my definition of error. All right, any questions about that? Geometric? Where to drop it? All right, so that leads you to the next question. Well, what if it's not geometric? Okay, well then that gets us to an alternating series. Okay, there's a special case for geometric series and there's a special case for alternating series. So if you notice that your thing is alternating, but the alternating has to meet some of the same requirements that we had. Okay, so here is how you'd recognize an alternating, right? The sign changes from negative to positive and then continues to change from positive to positive, etc. So we recognize that. But do you remember what other requirements there are for alternating series? Because that was like conditionally convergent. What were the conditions? Okay, they have to decrease. So each term needs to get smaller. Anything else? Okay, does it have to, and it has to get smaller specifically. Like it can't just get smaller to where the limit might be approaching 1. It has to get smaller to where the limit's approaching 0. So that's going to be important. So it has to alternate. The terms have to get smaller, and they have to get smaller in such a way that the ultimate term, the limit of the last terms would be 0. So that's your notes here. I've got those. Okay, those are the requirements. All right, we define error for an alternating series this way. Error is not equal anymore. Only a geometric one would have error equals this. For alternating, it's going to be error has to be less than. Okay, this is your only geometric will actually have an equal to. For alternating series, we say it has a bound. It means it can't be anything more than that. It's not even equal to. It has to be less than. And it's just less than the next alternating term. It's a super easy definition of error. So wherever you decide to truncate and cut it off, the error has to be less than the next term because all the other terms are going to get smaller and smaller and smaller and smaller. So this is the biggest it would be. The error will never be bigger than that. Because after that term, all that would happen would the next term would be subtracted, and then the next term would be added, and the next term would be subtracted, and the next term would be added, but you keep getting smaller and smaller and smaller and smaller. So this is the biggest it will be. That's what we look for. This is the largest possible value for error. It can never exceed that. That is the quote-unquote max. Okay, here is a Maclaurin series for a natural log. It is it's an alternating series. The terms get smaller as we go. And so it fits the alternating series definition. So it's kind of like a checkbox thing. Yep, it alternates. It decreases, but it only decreases if x is not bigger than 1. If x is larger than 1, then this thing will not decrease. which is why we are centered, it's a Maclaurin series, it's centered at 0, and our convergence is between 1 and -1. If x was anything outside of that, it doesn't decrease. But in this, when x is in between, it will decrease. So yes, it decreases, and the limit approaches 0, which is what I want it to do. As it decreases, it's getting smaller and smaller and smaller. You can check that because the limit of x to the n over n as n approaches infinity, it will get smaller assuming that x is a decimal. X must be a decimal between 1 and -1. If x is a decimal between 1 and -1, and no matter how high the power is, it's just going to get smaller and smaller and smaller and smaller. So this works. So if we want to truncate after the first 2 terms, then which is how that's defined, we just cut it off right here. So my error starts on that side of the truncation. And so my error formula is no more than the absolute value of that term. Because no matter what, the next term that you subtract would be smaller, and then the next term that you would add back would still be smaller yet, and the next term you would subtract would be smaller still, and the next term you would add. So it will be less than this amount. Okay, now we get to actually plug a number into this. They want us to evaluate it when x is the value of 0.1, which again fits within our interval, so x is 0.1. So then we'll say, okay, then it must be 0.1 cubed over 3. That must be 0.001 over 3, which is 0.0003 repeating. In other words, my error will never be more than 3 10,000ths of a decimal point. Yeah?
This might be a dumb question, but
Not at all.
how do you know x has to be between -1 and 9?
That's really, no, it is a great question. All right, so let's think about how x to the n behaves. Okay, so suppose x was something larger than 1. Let's just say 1.1. Okay, so say x was 1.1 to the n. In other words, that would be 1.1 to the first, plus 1.1 to the second, plus 1.1 to the third, plus. Okay, because I'm over 1, then when I square it, it will be big. These will all be bigger than 1. And so I keep adding and adding. In other words, it's not going to 0. When I square it, it's getting bigger and bigger and bigger and bigger. Okay, but say that you're less than 1. Okay, that would be 0.9 to the first, and then 0.9 to the second. Can you imagine what 0.9 to the second is? 0.81, which got smaller, didn't it?
Oh,
Okay, and then 0.9 to the third is going to be 0.027. No, 0.0,
0.36.
and it's going to get, sorry, not 0.1, 0.243.
Yeah.
Times 9, no, 729, 0.729, there we go, okay, 9 to the third, 0.729, which is smaller than 0.81. Like, they just keep getting smaller and smaller and smaller. Why again? Because this is 9/10. And if you square the power on the 9 is never going to be bigger than the power on the 10. The power on the 10 is going to get bigger than the power on the 9, and so it's because the denominator is going to grow bigger, then the whole thing is going to eventually get smaller. Whereas, what's the fraction for 1.1?
11.
That's 11 over 10. So now the numerator is bigger. So the numerator is going to grow bigger and bigger while the denominator, so it's always going to be bigger than 1. So the only way things will decrease to 0 like we want, we need them to decrease to 0, is for the x value itself to be between 1 or -1.
And this applies to all
Yeah,
That makes sense, thank you.
yes. Okay, so our error, the most it will ever be, is 0.0003 repeating. It will never be any bigger than that. Okay, so again, just to emphasize, this is not a formula for the actual error. It is an upper limit. It will never be more than that. Okay, it's a really important thing. Okay, never be more than that. Absolute value of a sub k plus 1. All right, so that leads us to our final question. What if the series isn't alternating? So it's not geometric and it's not alternating. It's just a regular old series, and it doesn't follow any of the other patterns. Okay, so enter the French guy named Lagrange, and he came up with a generic formula that works for all series. It looks, again, okay, look at that. It looks horrible. It looks horrible, but it's not. Okay, so if you truncate here,